Okay, so hello everyone. Today I'm going to give you a brief overview about the research paper called Why Systolic Architectures by H.D. Kuhn in 1982. So this is the outline of the presentation. But before going into details, I want to mention about the core motivation of this technique, which is why systolic architectures. So we can see that for systolic array, simplicity and regularity is an important principle, which is considered from the cost perspective. So in the paper, the author mentioned that cost effectiveness has always been a chief concern in designing special purpose systems. Their cost must be low enough to justify their limited applicability. So in other words, we know that for a special purpose system, its functions are limited, so that the cost must be kept low to overcome this disadvantage in order to be competitive. So Kuhn has divided cost into two separate parts, the non-recurring cost and the recurring cost. And for special purpose system, non-recurring cost is more determinant because recurring cost, which is the device part, are relatively the same for special and general purpose design. Thus, appropriate architectures are highly needed to lower the design cost. And moreover, in order to build fast computer systems with a limitation of component speed, improvement in computation speed can be achieved by the concurrent use of many processing elements. And also, the I/O considerations influence overall performance. Thus, it is necessary to balance computation with I/O. So we can see from this figure, the upper part is the model of the traditional computing system. A processing unit reads data from the memory, processes it, and then writes it back to the memory. So the biggest problem with this system is that the speed of data access is often much lower than that of data processing. Therefore, the processing capacity of the whole system is largely limited by the ability to access the memory. The systolic architecture uses a very simple method, which is let the data flow in the processing unit for as much as possible a period of time. So as shown in the lower part of the figure, the first data enters the first PE and is transferred to the next PE after processing. At the same time, the second data enters the first PE. So by analogy, when the first data reaches the last PE, it has been processed for a couple of times. Therefore, the systolic architecture actually reuses the input data for many times. Thus, it can be achieve high operation throughput while consuming less memory bandwidth. And to sum up what I mentioned before, a systolic system can be defined as a system consists of a set of interconnected cells, each capable of performing some simple operations. Information in a systolic system flow between cells in a pipeline fashion, and the communication within the outside world occurs only at the boundary cells. The systolic architecture has several characteristics. The first one, it is composed of multiple isostructure PEs, which can be one-dimensional, two-dimensional, serial array or tree structures, and nowadays we see more array forms. And the second one is the PE's functionality is relatively simple. The system improves the efficiency of operation by realizing a large number of PE's parallelism. And the last one is the PE can only send data to adjacent PEs. In some two-dimensional structures, there might also be diagonal data channels, but in most cases, it can only be sent data to adjacent PEs. And the data is pipelined to downstream until it flows out of the last PE. So it is not difficult to see that the systolic architecture is a very special design with simple structure and a low implementation cost. So in this paper, the author believes that convolution computation is an ideal application to show the characteristics of systolic architectures because it is a simple problem with a variety of enlightening systolic solutions. So, as shown here, the convolution computation is defined by the author. The problem can be viewed as a problem of combining two data streams, the sequence of weights and the input sequence, in a certain manner to form a resultant data streams of the result sequence. This type of computation is common to a number of computation routines. Like, for example, if multiplication and addition are interpreted as comparison and Boolean AND, then the convolution problem becomes the pattern matching problem. Thus, the architectural concepts for the convolution problem can be applied to these other problems as well. Other computation routines like filtering, pattern matching, polynomial evaluations, and so on. And the convolution problem is compute bound, since each input x is to be multiplied by each of the weights. If the x input separately form memory for each multiplication, then when W is large, memory bandwidth becomes a bottleneck, precluding a high performance solution. And as I mentioned earlier, systolic architecture can resolve this I/O bottleneck by making multiple use of each X fetched from the memory. So based on this, several systolic designs for solving convolution problems are introduced by the author. They also classified them into two groups: systolic convolution arrays with global data communication and systolic convolution arrays without global data communication. So for with global data communication, there are two techniques: broadcasting and fan-in. So broadcasting technique is one of the most obvious ways to make multiple use of each input element. And fan-in is the opposite, through which data items from a number of cells can be collected. So let's take a close look at the first design example. Broadcast inputs, move results, and the wait state. So in this example, the X value is broadcast to each processing element, and the W value is stored in PE in advance and remains unchanged. And the part of the result Y is transmitted to the right between P arrays in systolic manner, and the initial value is 0. It is not difficult to say that after 3 times units, the output of the rightmost P will be the first result of the convolution operation of the X and the W sequence. And then the Y value will be continuously output. And as for the one on the right, we have broadcast inputs, move weights, and the result state. Each Y stays at the cell to accumulate its term, allowing efficient use of available multiplier accumulator hardware. And by this way, it helps increase precision of results, since extra bits can be kept in these accumulators with modest cost. Then, for this fan-in example, if fan-in results, move inputs, and the weight state. The weights are preloaded to the cells and stay there throughout the computation. Results are finded in and summed using an adder to form a new Y. And when the number of cells, W, is large, the adder can be implemented as a pipelined adder tree to avoid large delays in each cycle. And so in the case of with global data communication, it is necessary to use the bus to broadcast data or the tree-like network to collect data. But when the number of cells increases greatly, the wires of such communication passes will become very long, which resulting in crowding out the space of other non-communication paths, such like the operation path, or having to reduce the clock frequency. So therefore, the design of without global data communication needs to be introduced, and which we will show next. So as we can see for the design R1, the result state, input and weights move in the opposite direction. So in order to ensure the one-to-one correspondence between X and W, the data in the two data streams will be input as an interval of 1 cycle. That is once every 2 cycles. This will result in only half of the cells are fully loaded. So two independent convolution operations can be interleaved to maximize throughput. And in this way, the cells needs to make some adjustments, such as adding an additional accumulator. And the following design at the R2, the result state, input and weights move in the same direction, but at different speeds. And for the design W1, the weight state, input and results move in the opposite direction, and the W2, the weight state, input and the results move in the same direction, but at different speeds. So these ideas are all similar and relevant to each other, which I will not explain in details for now. If you are interested, you can read the paper for more details. So once systolic design is obtained from a problem, it is likely that a set of other systolic designs can be derived similarly. And the challenge is to really understand precisely the strengths and the drawbacks of each design so that an appropriate design can be selected for a given environment. And after all these examples, we can be more precise in suggesting and evaluating the design of systolic architectures, which the design makes multiple use of each input data item. The design also uses extensive concurrency. And also there are only a few types of simple cells. Data control flows are simple and regular, as we shown in the previous examples. So in summary, systolic designs are simple, modular, expandable, and yet high performance. They therefore meet the architectural challenges for special purpose systems. And a unique characteristic of the systolic approach is that the number of cells expands the system cost and performance increases proportionally, provided that the size of the underlying problem is sufficiently large. And this is in contrast to other parallel architectures, which are solely cost effective for more than a small number of processors. So in general, rather than limited processing capabilities, bottlenecks to speeding up a computation are often due to limited system memory bandwidth. And the problem that was originally compute bound can now become IO bound during execution due to the result of mismatches between computation and architecture. Thus, we introduced the idea of systolic architectures, which ensure multiple computations per memory access and also can speed up compute-bound computations without increasing IO requirements. So the systolic approach can benefit not only convolution problems, as I showed before, but many other problems such as the signal and image processing, the matrix arithmetic, or even non-numeric applications. So within the development of systolic architectures, more and more special purpose systems will be feasible and will become applicable to many systems. and especially systems that implement fixed and well understood computation routines. And so that's the end of this presentation, and this is the reference paper. If you are interested, you can like read this paper into more details of like each examples of the idea. And thank you for your time, and thank you for listening.